Genuinely, why?
How we doing?
Good.
How about you?
How about you?
Okay.
Just okay?
So
How was your weekend?
I don't know, I blinked and it was gone.
Real.
Yeah,
We're
feel
excited
bad.
to see you all. Alright,
No?
that was more of a anything special for midwinter break?
No.
Just chilling.
Catching up on your sleep.
I have some papers to grade. Speaking of papers to grade, what haven't we done yet for this chapter? Do we do every chapter?
A test.
Homework quiz.
Oh, don't say it's today.
No, you're not.
There was no answer.
Oh!
You're saying like next class.
I can't say anything if everyone's gonna be shouting things at me. We do it next class,
Okay.
so it's coming.
Okay, that's fine.
Thank you.
So we
We've had numbers 1 through 5.
all right. So how's the homework been going?
I haven't done anything. I didn't know we had anything.
Okay. So I've assigned like up through 35, basically.
Yeah.
When is that due?
Sunday.
Next Sunday?
This Sunday.
It wasn't on my name.
As in like 4 days from now? I think it's on there.
No, wait, what? I thought it was due this.
No, it's when this Sunday comes up.
Oh, okay.
This Sunday.
Yeah.
Right? Like that's how we use that phrase, like talking about
Well,
the
I was thinking about like this Sunday because it's like the start of this week.
that'd be last Sunday, because it's in the
Okay, yesterday, Sunday. Or 2 days ago.
Yeah, that's okay.
Wait, what day is it?
Today's Tuesday. I know, it's hard. Are there questions from homework that we want to talk about?
Let me consult.
Sure, go ahead.
Question. Was the stuff that was due 2 days ago on my note today?
No, nothing was.
No,
Okay, I didn't think so, but
Yeah.
that's what we were talking about
Yeah,
before class.
correct. There's nothing that's been done. Yeah. He probably just did the 1 through 15.
Yeah,
Ish.
that wasn't due.
Not yet, but it's due eventually. You know, so.
For fun. Be those bored.
I rushed and did it again.
Well, you know what? It's one less thing for you to do for this Sunday, right? There's no harm in doing it early. That's great. What'd you guys find? Dan?
I had a question about the homework quiz in general. Is there gonna be like a question that says like, evaluate the function in like a specific type of division?
I would tell you you should definitely use your calculator. What do we have to find using our calculator so far?
Like numbers.
The zeros in the extrema? Definitely should know how to do that.
I remember.
There's a hint.
Yeah, I kind of remember that.
And
Kind of remember.
the max. Wait, and the max and the minimum.
That's the extrema. Yeah, max and min are extrema. Yup, that stuff. Should definitely be able to do that.
The zeros, we don't have to do like all the synthetic division, we can just find.
Depends on what the directions ask for.
It's not gonna be one of the ones where you can keep going, yeah, like the one.
Mr. Mutters, he made us do that like by hand. We had like, he gave us the problem, no calculator, we had to do the synthetic division all by hand.
Yeah.
To find the zero.
Like I showed you, like that's how I had to do
The
it.
PQ list, we had to go through every single number. Like that.
Like I showed you in my example, where it's just like you just keep going until you get one that works.
Oh.
And once you have one that works, maybe things go a little bit smoother, but
We're not gonna, it's not gonna be like that long though, right? It'll be.
I would not require you to do any of these problems with no calculator assistance in terms of finding a starting place. We're gonna talk about how to do that a little bit more today. Okay? If nobody's got homework questions, then I'm just gonna kind of get into it. Is that okay? So there's like a stray problem type that got assigned, we haven't talked about how to do. So if you guys looked at, what is it? It's like 13 and 14. I think I assigned this, or
Yeah.
but we haven't talked about how to do it yet. Let's talk about how to do something like that. So there's two main theorems that we're going to use in order to do this. One is called the irrational conjugates theorem. So our irrational conjugates theorem says for polynomial with integer coefficients and irrational 0, a plus c times square root b, then a minus c times square root b is also going to be a 0. When you have two expressions like this that differ by that sign in the middle, those guys are called conjugates. Do you remember that from Algebra 2? Or term conjugates. So these are irrational conjugates. The same thing holds for, we talk about complex conjugates. So the complex conjugates theorem is basically the same word or same thing. I've just changed three things. Instead of rewriting it, I just wrote it above it in a different color. I'll pause here. I'm going to take a minute to write these things down, and then we'll put these into action to do some examples, okay? I'll do that. It's clear that why I wrote conjugates there is what that means. Okay, everybody get that I wrote two theorems here, where the only difference between the two theorems is the green is the second theorem.
Is it A minus I?
Yes. Where I is that complex, or that imaginary number, square root -1. Actually, yeah, that's fine. I'll do a second example. Let's, so our example says to write a polynomial with integer coefficients and minimum degree that has the zeros x equals a half, x equals square root 2, and x equals 1 minus square root 3. Now, because of the irrational conjugates theorem, I know there are two other zeros that must be on this list. The conjugate to the square root of 2, and the conjugate for 1 minus square root 3. What is the conjugate for square root 2? Guys, it's negative square root 2. What's the conjugate to 1 minus square root 3? 1 plus square root 3. Is everybody okay with what I did there? Okay?
Do you have to do it for the half?
Is that an irrational number?
No.
Then no, I do not. Is everybody good? Okay. So I know that my polynomial that I'm going to write has all of these 5 zeros. Everybody okay with that? So what I'm going to do is I'm going to convert each of these solutions into a polynomial by subtracting everything to be on the same side as the x. Now notice when I subtract over like the 1 minus root 3 and the 1 plus root 3, I'm going to think about subtracting that over as just one number. It'll be clear later why I'm going to think about it to do it that way, but it's basically to make some future calculation a little bit easier to handle. Is why I'm going to think about it that way. It would not be wrong, for example, to have written instead of x minus parentheses 1 minus root 3 to have written x minus 1 plus root 3. Not wrong to do that, but I get some benefit from doing it the way that I'm going to do it, and I'll point that out later when we get to it. Is everybody okay with what I did here? I just added and subtracted things from both sides to get everything equal to 0. So since each one of these 5 polynomials is equal to 0, if I multiply those polynomials together, what are they still going to equal?
0.
0, right? What does that guarantee for me then? That this resulting polynomial will have the real zeros. Oops, that's supposed to be plus. On this list. Is everybody good so far? Now all I need to do now is to multiply this out to get that polynomial that I need. Well, almost. Everybody so far so good? I want to zoom out here for a second and just talk about what we've done. So for integer coefficients, I had to include these guys, and I need to include one other thing. Do I have any non-integers in my zeros? 1/2, right? That's not an integer. Guess what I'm going to do with that? I'm just going to slap a 2 out front. And that, when I distribute that through, that'll get rid of any non-integer coefficient. Everybody's good? So we've taken care of that. The minimum degree, how do I handle that? Did I include any zeros that didn't have to be there? No, right? I just used the zeros that I had to have. That's the minimum degree. As long as I don't do anything cuckoo, like include stuff on there that doesn't need to be there, I handle the minimum degree part. So far, so good? Okay. Now all I'm going to need to do is multiply this out. Now, the order in which I'm going to do my foiling, I'm going to be very careful about, because this can become a really big mess if I'm not careful about it. The polynomials that had the conjugate pairs are the ones that I want to multiply together. Everybody so far so good with this? And then I'm going to distribute the 2 through this guy. What type of multiplication pattern do I have here with x minus root 2 and x plus root 2? It's a difference of 2 squares, right? Do you guys see that? So I have a plus b times a minus b. When I multiply a difference of 2 squares together, I get a squared minus b squared, right? So I'm going to get then x squared minus square root 2 squared. Could you FOIL that out instead? Sure. Are you going to get the same thing I did? Yes. Is all I'm doing there trying to save myself a little bit of time and a little bit of writing?
Yes.
Yes. Do you have to do it that way?
No.
No. Everybody feel good?
Yes.
This one, we do have to FOIL, but there is going to be a difference of 2 squares in there eventually. So x times x is x squared. Then x times negative 1 plus root 3. I'm going to just write like that. Everybody okay with what I did there? I'll do the same thing. So far, so good. Any questions to what I've done? I'm going to continue just kind of simplifying things. So square root 2 squared is just 2. Now here I'm going to distribute the x through and distribute the negative through. Everybody okay there? I'm going to do the same thing at the other piece. Is everybody okay still? Now I'm going to multiply 1 minus root 3 and 1 plus root 3. To multiply that out, I have to FOIL, or what kind of multiplication pattern do you notice? A difference of 2 squares, right? I have an a minus b times an a plus b. So again, I could FOIL that out, or I can take advantage of the difference of 2 squares that I see there and just try to make my life a little bit easier. So far, so good. Now I'm going to clean some stuff up in here. I'm going to combine some like terms. So notice I have a negative root 3x and a positive root 3x. Those guys cancel out, right? Then I have an x squared minus x, and minus x is minus 2x. And then 1 minus 1 squared is 1. Square root 3 squared is 3. 1 minus 3 is negative 2. So far, so good. All right, I'm going to continue foiling now. I would probably choose to FOIL these two together. So when I do that, I'm going to get 2x cubed minus x squared minus 4x plus 2. So far, so good. Now I just have to multiply these last two together. Now, when I have two things that aren't binomial, and I'm multiplying them together, I'm still basically doing the same thing as FOIL. I'm making sure that each term in the parenthesis on the left multiplies each term on the parenthesis on the right. So like, I got to do that. Is everybody okay with how I multiplied that out? My last step then is to just combine my like terms together. So I have only 1x to the fifth term, and I have a minus 4x to the fourth, and then minus 5x to the fourth, and that's all my x to the fourth. So I'm going to cross them out as I transfer them down. And I have a minus 4x to the third. So now I'm down to minus 1x to the third, and then minus 5x to the third. I meant 6. Sorry. Addition and subtraction. 2x squared, 8x squared, and a 2 more x squared is 12x squared. Then I have an 8x minus a 4x, and then a minus 4. So that's my polynomial. Now this is an awful, tedious, huge, terrible example. They won't be this bad in homework. I just wanted to make sure to kind of cover a situation where we had like a plain radical and then like a radical expression in the same problem. On a homework or a test, you'd probably have one or the other and not both, because it's like gets pretty overwhelming. Daniel?
Yeah, use that.
Sure. Is everybody okay with how we got to that final answer there and stepping through the process? I'm going to do kind of the same sort of example here with imaginary things now.
go.
Big fat fail, so way to go. I'm so sorry. All right. Same sort of problem, right? Initial setup identical. I want to start by looking at my zeros. I see an imaginary or complex number here. So again, I know that its conjugate also must make my list. Everybody's okay there? And then I will turn these all into polynomials. Everybody feel good there? Multiply them all together. Notice here I don't have any fractions anywhere, so I don't have to multiply through by a constant this time. Yay, us! That was so hard. Did I need to have all these 2's? Right? I have the same solution or the same zero happening 3 times. Do I need it 3 times?
No, I could have substituted.
Yes, you need to have it 3 times. It's got to show up 3 times, or else your polynomial will only have 1 of them instead of 3.
Can I move that?
All right. It's time to just start foiling. So x minus 2 times x minus 2. I'll do that. And then these guys I'll multiply together. And then we'll FOIL again, so I'm going to have x cubed minus 2x squared minus 4x squared plus 8x plus 4x minus 8. And then we'll distribute some stuff through here, so I have a minus 2x plus 3ix minus 2x minus 3ix. Plus, I have a difference of 2 squares here. So I'll use my difference of 2 squares factoring pattern on that guy. Combine some like terms. Those guys canceled out. 2x and 2x is minus 4x. And then what's 3i squared? 3i times 3i.
Is it after birthday?
So that's that, right? And we remember that I squared is negative 1. So plus 13 at the end. And then I just FOIL this stuff out. And I'll be done. $78. Is 156. Should be squared. And then my last one was minus 8x squared plus 32x minus 104. And then collect some like terms together. That guy's done. And then this guy and this guy, that's minus 10. And this guy, that's 37. And that's 49. And then negative 78. And that's 80 and 50 is 130, 126. And then 134. 156, that's plus 188 minus 104. Again, assuming I didn't make any arithmetic errors, which I was trying not to, but like, heck, it's the end of a long day, so like, fire aware. Everybody okay here? So I think those happen in the homework. We have another theorem called the fundamental theorem of algebra. I just abbreviate that as FTA, fundamental theorem of algebra. It says two things. And the second thing it says is that the number of solutions is, number of complex solutions is equal to the degree, provided that we're counting multiplicity. So if a solution is used twice, it counts for two solutions, even if it's the same number. Everybody okay there? Okay. So we have two small problems when it comes to finding all the zeros, not just the real zeros for our polynomial. If we're going to use the graph to help us shortcut through our synthetic division and pick the stuff we need, we have two things that are going to be kind of invisible to us. Imaginary solutions, totally invisible, never going to be able to see them on the graph. The graph gives us nothing about the imaginary solutions. The other thing, though, is the multiplicities, which the graph can tell us about. And the last theorem we're going to look at here is, I call the bend bounce straight theorem. And says, yes.
I wrote that.
Sure. So there's three things. If the zero for a polynomial bounces, there's a picture of what a bounce would look like, where it hits the x-axis and rebounds without really passing through it. That zero has an even multiplicity of at least 2. The next is bends. Write it this way. So this is an example of a bend. Notice how this part of the graph is like a cup, but this part of the graph's like an umbrella, like a hill. That point there is called an inflection point, where it changes from looking like a cup to a hill. That's what a bend looks like, is where you have that change. That zero has an odd multiplicity greater than or equal to 3. So 3, 5, 7. We don't know how many times it's going to be used, but it's at least 3. And it's odd. And the last possibility is it goes straight through. If the zero goes straight through, that zero just has multiplicity 1. So, what we can do then is we can take all this stuff together and use it as part of our detective work in finding all the possible zeros for our polynomial. So we can use our rational roots theorem to get a list of all our possibilities. We can then pare that list down by looking at the graph and where the x-intercepts are. If the approximate x-intercept is equal to something on the list, that's a candidate for synthetic division. If that x-intercept is a bend or a bounce, I know I'm going to be able to do that synthetic division more than one time. So I could do it multiple times. That'll help me pick up the multiplicities. I'm going to keep doing my synthetic division until I get down to a, what's up? Sure. Until I get to a polynomial, a quadratic. And then I'll use the quadratic equation to finish it off in case there are any imaginary solutions at the end. The quadratic equation can pick that up. Or quadratic formula, excuse me. Everybody's okay? What you'll never encounter in this class is a case where you have 4 imaginary solutions. Actually, I shouldn't say that. I could give you one that has 4 imaginary solutions and be okay. You just do it by factoring. You wouldn't have to do the polynomial division to do it. So, at this point, let's just do some examples, okay? And we're going to kind of paste all this process together. So let's say I want to find all the real zeros for this polynomial. Stupid thing. Okay. All right. So the first thing I'm going to do is using the fundamental theorem of algebra. How many solutions am I looking for? 4. Using my rational, my possible rational zeros, I need the factors of 35 divided by the factors of 8. So the factors of 35 are 1, 5, 7, and 35. And my factors of 8 are 2, 4, and 8. That all look okay? I'm now going to pare this list down because, shoot, Mr. Luke, there's 32 things on there, and some of them look pretty gross to try to do semi-synthetic division on by looking at the graph. So on my calculator, I'm going to type in y, press y equals, and type in my polynomial exactly as it's written on my sheet of paper. God bless you. Everybody's good with what I did there? I'm going to graph this. To graph it, I'm just going to do zoom standard. And I'm going to look at my x-intercepts now. So each tick mark is 1, right? So this one is something little less than -1, but bigger than -2. So I'm going to go ahead on my list, and I can get rid of -5, -7, -35, -35 over 2, -7 over 2, -5 over 2, -7 over 4, -35 over 4, -35 over 8. And then I know that it's less than -1 still, so I can get rid of -1/2, a -4, -8, -5/8, -7/8. So I'm left with -5/4 as really my only likely candidate for this first one. Is everybody okay with how I did that? Or if I looked at the other one, this has to be a number between 0 and 1, right? So I can get rid of 1, I can get rid of +5, +7, +35, +35 over 2, 7 over 2, 5 over 2, 5 over 4, 7 over 4, 35 over 4, 35 over 8. And then maybe have to keep all the rest of them. But we pared that list down substantially. If you're to estimate what this one is, it's probably +1/2. But I'm going to do the -5/4 with my synthetic division because I'm quite positive that's what it has to be. This one, if it was 5/8, that wouldn't shock me instead of 1/2. That's pretty darn close. I don't know if I'd be able to tell the difference. Is everybody okay with my selection process? I notice that they're both straight. So how many times should those x-intercepts be used? Just one time. How many solutions do we see on the graph then? 2. Where are the other 2? Because there should be 4 total. If I can't see them, they must be imaginary. So I'm going to have to catch those with the quadratic formula at the end. Everybody good for our plan? All right, let's start ripping and rolling. I decided to do -5/4. Now, really, when I do that, I'm going to think about like -1.25 is fine. And then I need those numbers. What am I being careful to double check as I write those numbers in? What am I being careful to check?
Oh, that there's everything.
That every degree is covered, right? I go from fourths to thirds to seconds to firsts to constants. Yes, no extra zeros needed. Got to be really careful about that. Do you think Mr. Gould's going to pull that sneaky jerk trick on a test or something?
Oh, yeah.
Why would put it past him?
That's not.
Definitely not. You don't know me that well. All right, I bring my 8 down, I multiply that by -5/4, and I get -10, -36. I multiply by -5/4, and I get 45. And I add that down as 72. I multiply that by 72, and I get, oh dear me, 18 times 5 is 90. That's -28. And I multiply that, get +35. Woohoo! That's what I'm talking about, guys. Yes! Lily, what's up?
May I go to the bathroom?
Sure. So, again, this is my remainder, constant x, x squared, x to the third. So what I've shown here is 8x to the fourth minus 26x cubed plus 27x squared plus 62x minus 35 factors down to be x plus 5/4 times 8x cubed minus 36x squared plus 72x minus 28. Everybody okay with, I'm just writing out some extra steps to give you a clue for like, you can get a feel for what's just happened. If you don't write it out, sometimes it's hard to see. If I look at the coefficients on 8, -36, 72, and -28, what do you notice? Greatest common factor of 4. Oos. Let's take that out. We'll make the synthetic division a little bit neater on the next round. And I'm just going to go bloop, bloop. Okay. Now, my other rational zero that I had to work with was this guy. We figured it's either +1/2 or +5/8, right? Those seem like the two most likely, eyeballing that. Which one do you think Mr. Kulik's going to want to start with? The easier one to do the calculation with. I'll do the half. Notice that I didn't have to do another possible or rational zeros calculation for the new polynomial I have. The old one will still work because any zeros this one had, the original one had, because I know it's a factor. So I just rip through this guy real quick. Oh yeah! So I have 4x to the 5th times x minus a half times remainder constant x squared, 2x squared minus 8x plus 14. If you look at that third polynomial, 2x squared minus 8x plus 14, what do you notice about its coefficients? 2, negative 8, 14? Greatest common factor of 2. I'm going to pull that out, and guess where I'm going to push it through? Whoop, whoop. Do that guy. That's a 4. What I've done now is I've factored that. So I'll just set him equal to 0. I got this guy, but I know that guy's solution. It's negative 5/4. I found that already. I'll set that one equal to 0, but I know that solution. That's the positive 1/2. I got that already. And I'll set the last guy equal to 0. That guy we don't know. What kind of solution do I expect this to have? Imaginary. Why? Because I didn't see any other x-intercepts on my picture when I looked for it. So it's just the quadratic formula for me. If you don't remember the quadratic formula, shame on you. That's something eventually you should probably commit to memory. Your college professor will certainly expect that you got that memorized.
I have it memorized.
Excellent. Negative b plus or minus square root of b squared minus 4ac all over 2a. Yeah, you can set it to the fight song, right? Yeah, I'm not a singer. You can sing. I'd love for you to sing it to everybody. But that's just like, it's not me. I'm no rhythm, can't carry a tune, can't sing on key. Like, that's not my learning.
That's tough.
I know.
You ever tried?
It's just a fail.
You need to teach me.
How do I reduce the radical negative, or square root of negative 12? Who can do it in their head?
You can pull out a 2, right?
2i square root 3. 12 is 4 times 3. 4 is a perfect square. The square root of 4 is 2. And the negative makes the I. And then I can reduce this, right? I can think about this as like 4 over 2 plus or minus 2i root 3 over 2. So 4 over 2 is just 2. 2i root 3 over 2 is just I root 3. So that's 1, 2, and then because of the plus or minus, solutions 3 and 4, and we are done! Now, how many of those do you think I can realistically put on a test? 1 or 2, right? Like that's kind of the top.
0.
The most I could ask you to do. Because that's, even on that, which is a fairly straightforward example, it takes some time.
Yeah.
Right? Like there's a lot of steps, there's a lot of things to remember to do. So we've just built out this other factoring procedure, right? So you remember way back in the first lesson where we drew this factoring tree? And I said, oh, look at all these little stop places. These are no longer stops. We have something else we can do, right? We can synthetic divide it. We can factor some more stuff out. If we can't make that work, then we stop. We're still stuck. That's not an end-all, be-all. It's going to work every single time, but it can work in those situations where it doesn't up here. Is that okay with you guys?
Yeah.
Yeah. And I think technically it has to go here too. I forgot that one. To highlight it. But that now gets plastered onto our factoring tree that we had built before. That synthetic division procedure we just went through can now get scaffold on top of that. If you keep studying mathematics long enough, there's other stuff you can scaffold on top of that. Because factoring polynomials is kind of actually a rather important topic in mathematics, has a lot of application into really important and valuable real world problems like cryptography. If you don't know what cryptography is, you should. So you know, like you have a cell phone, right?
Yeah.
And you're sending messages across the public network,
Yeah.
right? Ideally, anybody that wanted to could intercept your message and read it.
I do that all the time.
The reason that they, even if they can intercept it, they can't read it because there's an encryption going on. They've encoded your message so that unless you have the key, you can't open it to read it. Now your cell phone does this all automatically. One of the methods of encryption is built around being able to do a factorization of large numbers. So like finding the divisors of two large numbers, like 1,000-digit numbers or 10,000-digit numbers, which there is not a fast procedure to, but this idea of factoring polynomials is directly applicable to the methods you might use to factor a number. And if you are able to decode somebody's private messages rather quickly, you can imagine all sorts of entities that would be very interested in that technology, like the federal government. Not necessarily to use on its citizens, but it does. But to use on enemy nations for spy purposes. Yes, go ahead, yeah. Anyway, so that's a brief aside to just give you an idea, like, hey, this thing you're doing is actually, you know, like the tip of some very large iceberg that ends in a very valuable technology. What do you guys think? Are we okay? Okay, this will allow me to sign the last of these problems, so we can assign now up to 53. Boo, I know.
No, I said boom.
Boom, okay, goes the dynamite.
Yeah.
That set won't be due until the end of break. That feel fair? So the 1 through 35 this Sunday, the other set the following Sunday, so it gives you a little bit of time in between your trips to tropical locales.
It's the sort of viewers do next, not like this upcoming time, but the week after. Is our test this week or is it going to come back?
Let's think about that. The test won't be this week. Let's not do that. We'll do the review day with the homework quiz next class, and then maybe I'll decide on what we want to do the day we get back. We'll probably have the test the day after, the class after we get back. Because I don't think that's setting you guys up for any kind of success, trying to have the test the day you get walk in from break,
Yeah.
right? Like that feels like just a recipe for a lot of sad students.
Wait, can we do a take-home test?
Ooh, that's great. A take-home quiz.
I'm good. I mean, I could think about it, but it's going to be way harder than it would be in person. Like, it's a very different kind of test if it's going to take home.
Can we do take-home homework quiz? Yeah, that's a good.
Well, again, like, that's a very different assignment that I'd be writing. Where it has to be individualized, has to be difficult to AI cheat through it.
Not
So-
too difficult.
I would conceptualize it a very different way, where it would be a different set of skills.
Square.
Then the stuff that I would ask you to be able to do without. I think you're probably better off doing it without help.
Should you like a partner quiz?
Guys, you don't want to burn that on this. It's literally like, do not use your calculator is the homework quiz. You know that we're not gonna do like partner homework quizzes the whole time. We should save that for when we get to a topic that'll be challenging enough to where like having another person would help you. Rather than like, do not use a calculator, which is kind of what we're at here.